to do in our lab. My name is Tim, and I will introduce today ProteinShake, which is a Python software package that we are currently developing, which serves both as a collection of datasets and benchmarks for deep learning on protein structures, as well as a framework for unifying and standardizing the processing steps that are necessary to transform raw protein structure files into formats that are ready for deep learning. Typically, when you start a machine learning process, the first step is to prepare your data. This entails downloading, reading, parsing, cleaning, converting, and storing your files, as we've seen before as well. When working with proteins, that might be a little bit more cumbersome than working with, let's say, image data or natural language, for example, because there's several layers of information. Yeah? You have atoms, you have residues, you have primary, secondary, tertiary structure. And also the labels that you're working with can be non-trivial to parse. So think of ontologies, for example. Another consideration that you have to make very early on is the representation of the protein that you're choosing, which depends on the deep learning architecture that you're working with. You might be using a model that can utilize directly the sets of coordinates from the protein, such as PointNet, for example. Could also be working with a convolutional neural network, which requires a voxel grid representation of your proteins or rasterized version of the protein structure. Or you're working with a graph neural network, which requires then a graph representation that's derived from the protein structure. So this adds another step to your pre-processing. And along the way, you have to make a lot of decisions. You have to set a lot of parameters. And I can guarantee you that if you give the same data to different research groups and you let them process the data, you will get very different results. So there's also a reproducibility issue here. Overall, the data processing with protein structures for deep learning can be very tedious, which is why we created ProteinShake, which now takes care of all of these steps for you. The design goal of the library was to provide protein structure datasets in the most simple and accessible way, such that practitioners can focus on prototyping and developing their models. And it doesn't get more simple than a single line of code that you see here, which is how you use ProteinShake. It consists of 3 parts. First is choosing a dataset with labels of interest. You then convert it to one of the representations that you are working with. And finally, you load it into data structures that are specific to your deep learning framework. It's another level of the processing, right? There's people that work in TensorFlow, people that work in PyTorch, graph people have their own libraries, and so on. So this is something that ProteinShake also takes care of. So no matter what background you have, what representation you want to work with, what frameworks you're working with, and which representation you like to use, there's a good chance that you can use the ProteinShake datasets in your work. Another very critical aspect of a machine learning project is the model evaluation. In the context of proteins, models can be evaluated on a variety of tasks and applications. You have classification, regression, it goes into inverse folding, stability prediction on pairwise problems, such as protein-protein interaction. Each of these applications require different preparation of your data. So, for example, are you working with a single protein as an input or a pair of proteins as an input? Are you working with a classification on the residue level or on the protein level? Yeah? All of these require different processing steps, which again, fear not, ProteinShake is taking care of. The thing about proteins that you're probably all aware of that you have to take into account is the inherent similarity between proteins. This is important when you do your train test and validation splits, because if you would just do a random-based split, there's a good chance that you end up with very similar instances in your train and in your test set, which would then give you a poor estimate of the generalization capabilities of your model. Which is why people typically employ some sort of similarity-based split that is usually defined on sequence similarity. Now, we newly propose also a structure-based similarity split, which is quite heavy to compute because naively you would need to do all pairwise structure alignments and comparisons. We use an efficient algorithm for that, actually from the lab that just presented before. And we also pre-compute all of these splits and host them such that you can just download and use them in a matter of seconds, essentially. So ProteinShake also takes care of the entire evaluation pipeline. This is sort of like the bird's eye view of the library. It consists of 2 main classes, that is the dataset class and the task class. Those are intended to tightly wrap around your model and abstract everything away that is not your model so you can focus on developing it. We have the dataset class, which takes care of preparation and processing of the model, so downloading, reading, parsing, converting, storing, etc. And it also prepares your data as an input to the model that is converting it to one of the representations and loading it into your deep learning framework that you're using. On the other side, we have the task class, which provides train, test, and validation splits, as well as appropriate metrics collected from the literature. We do have a leaderboard online, so if you use ProteinShake to evaluate one of your models, please feel free to share the results there and let others compare too. To make this a little more tangible, I have a code example here, which is how you would make a machine learning project in ProteinShake. You start by preparing your data, which is this single line of code that I showed before. You select a data set with labels of interest, you convert it to a representation, and then you load it into your framework. You then come up with some sort of model that you would like to test and work with. And you can use the train, test, and validation splits provided by ProteinShake to feed them directly into the native data loader of your respective framework. After some model training, you can then obtain predictions and also evaluate these predictions, again, in a single line of code with ProteinShake evaluators, which will yield a set of relevant metrics for the task that you're working with. That's it. This is not pseudocode. This is actually working code. So you can copy and paste this, and it will run through. So all that is left to do for you, basically, is to develop a model. And then ProteinShake will take care of the rest. We already implemented a broad range of tasks that are available in the library already. We have classification tasks based on the gene ontology, enzyme classes, and structural folds. We have regression problems. We have pairwise problems, such as protein-protein interaction, protein-ligand interaction. We have ranking, regression, retrieval, 3D alignment, metric learning, pre-training. There's really a lot that you can do with ProteinShake already. And we're actively working on extending this in the future even further. And we also hope from community efforts to contribute to the library. It is now very easy with ProteinShake to compare different models and architectures across all of these tasks and representations, which is why we implemented a couple of baselines to showcase the capabilities of our library. What you see here is one baseline model for each of the representations. We have a graph-based model, a point cloud-based model, and a voxel model. And we evaluated them on all of the tasks that we had implemented at the time. The best results here are highlighted in bold, and there's an interesting observation that you can already make, namely that there is no such thing as an optimal representation or architecture for each of these tasks. In fact, you might want to choose a different representation or a different architecture depending on which task you are working with, which is intuitive as each of these representations capture different aspects of the protein structure. Graphs, for example, are very good at modeling interactions and so on, but maybe lose a bit of the geometric information, which might be better modeled by a point cloud or voxel model. We also looked at the different data splits that we are providing. We have a random sequence-based and structure-based similarity split. In each of these subfigures, you see one of the tasks, and we applied all of the three models to each of the tasks. Color-coded, you see the random sequence and structure-based split, and you see pretty much the same pattern across all of these plots. That is that these splits get progressively harder to generalize to for the model. Also, this is something that you might want to consider before starting your project. If you expect to apply your model to novel folds and structures, for example, it might make sense to also train and evaluate your model on a structure-based split, which is then now available with ProteinShake. We also looked at pre-training, which is becoming more and more important. It was already hugely influential on sequence-based models, and it's also getting a lot of traction in the structure-based modeling domain. What we did here was to employ a simple residue masking strategy that's very simple, very similar to what's being done on sequences. And we used the AlphaFold SwissProt dataset for pre-training, which is also provided by ProteinShake. We have the three models here again. The red line in the middle denotes the model without pre-training, and then the further you go to the right, the more the model improves with pre-training. And you see that in most cases, so most models and tasks, pre-training has a very positive effect on the performance of the model. I should note here that there's other pre-training strategies, and we did not explore further any of these because we just wanted to make a point here, but those could potentially improve these results even further. So those are just three little insights that we gained from playing around with ProteinShake. But we hope that due to the simplicity of access to the data and the comparability between all of these architectures and tasks, that the library will facilitate the generation of new insights for hopefully many researchers in the future. I want to close the talk with a note on the future of the library, where we are going, and also how people can contribute to the library. Because I said initially that ProteinShake is not only a collection of data sets, but also a framework for processing and standardizing the processing of the data, which is why we put a great emphasis on extendability as well. We did not only want to simplify the access to data sets, but we also wanted to simplify the process of creating new data sets. So here we have a code example of how to create a custom data set in ProteinShake. Maybe in the last rows you cannot see that too well anymore, but it's not so critical. Basically, most of the work is being done in the first line of code here, which is where we subclass the ProteinShake dataset. This takes care of all the boilerplate code of reading, parsing, filtering, converting, etc. Your data. All that you have to implement is the logic that is specific to your dataset. That is where to find and download the raw PDB files, which is the first class method here, and then how to add annotations and labels to the proteins, which is the last class method here. Similarly, a task is implemented with a few lines of code with subclassing the ProteinShake task. You then define a few key properties, such as the type of the task the dataset is based on, what inputs and outputs look like. And then you define a target prediction label, which is obtained from the annotations that we added earlier to the dataset. You also define a set of relevant evaluation metrics, and with that, you're done. With just implementing these two bits of code, which take roughly half an hour to write down, you have created an entirely new custom dataset and evaluation task that you can now instantly make available to a broad range of researchers. Because anyone can use your data now in any representation that they like, with any architecture that they like, and with any framework that they like. We link a great deal of other resources on our website, ProteinShake.ai. We have the GitHub repository there. We have the documentation, the leaderboard, tutorials, and everything to get you started. You can also just go ahead and try yourself. It's available on PyPy with pip install ProteinShake. I want to emphasize that we are very happy about contributions, also feature requests and bug reports. This is in a very early stage yet, and we are especially looking forward to contributions from the community. There's probably two ways of how you could contribute. For example, you are a structural biologist and you have data laying around that might be a very interesting machine learning problem. Please feel free to create such a custom data set and publish it on the ProteinShake repository, and you will instantly make available your data to a broad range of machine learning researchers. Similarly, if you're a machine learning researcher and you have a model that works very well on protein structures, please feel free to use all of these tasks that we have available to benchmark your model and to share your results on the leaderboard, such that others can compare to it and easily identify state of the art. That was ProteinShake. Thank you very much for listening. I hope there's time for some questions, one or two. Otherwise, you can hit us at the poster tonight at A21, I believe. Thank you very much.
My question is how these data sets that are already present there, how are they kept up to date?
We do have an automated release pipeline. So all of this is scripted, and we have a cron job that basically updates this every couple of months. We do have a versioning system, so you have different versions of the data set that you can use. We hope that we do not get too many different versions, such that we can compare still on the leaderboard. But yeah, we take care of updating the library. And as I said, I hope that we can largely give this in the hands of the community soon, such that this can grow And I mean, we will still be around to maintain the library, but there's only so much we can do as individuals. So yeah, that's that. But we take care of updating the releases. Yeah.
Okay, thank you for your talk. It's a very good tool. I have a question about your representation. Are they invariant representation, particularly in case of the voxels?
No, you have to take care of that yourself. I guess in most of the cases. So the voxel representation in particular is not invariant or equivalent to anything.
So one improvement that you can add if you voxelize the
Yes.
representation, you can make it invariant, because this is coming from your representation and you can add.
Yes, absolutely. So this is more or less the start of what we are trying to work with. We try to keep it simple to have the whole thing done, but we are working on other representations as well. That would be one way, definitely, and we're looking into that. Thank you.
And are you looking for to add for your application yet the prediction of the stability of the protein or binding affinity between protein-protein interaction?
Yes, so this will be once part of a data set as a prediction problem, and then also as part as a feature. So from the files you can extract parameters and metrics for each of the residues, for example, as a sort of quality control for the AlphaFold data sets. You have the PLDDT as well. So these kind of things are added partly and will be added in the future very soon.
Hi,
yeah.
Thank you very much, talk. Very useful toolbox. I have a question about the structure-based representations, particularly for protein interactions. Does your library allow you to select the biological assembly or different representations in the context of the crystal binders?
What do you mean by selecting? So, I mean, the problem or the task that we have here is formulated as you have two entities that interact in some way with each other. We randomly rotate and translate them, and then the task is to predict whether those two interact or not, and also where these binding residues are. But the trick about ProteinShake is that you can pretty much formulate this however you want. So this is just one of the tasks that we provide initially, but the idea is that you can formulate any kind of prediction problem that you would like with very few lines of code and utilizing the boilerplate code that ProteinShake provides.
Yeah, but the thing is, if you have, if you want to annotate protein interactions from the crystal structure, the coordinates in the crystal structure might not correspond to the biologically relevant interface. Or the
okay. Yeah, we interfere interfaces, or we influence interfaces by like rolling a ball across. It's basically a radius. So any.
Also, okay, let's discuss this.
Yeah. Okay. Very welcome. Yeah.